Imagine you are trying out this massive new trend in app development. It's called vibe coding.
Oh, right, the famous vibe coding.
Right. So you're sitting there utilizing natural language, just asking an AI agent to build you a website.
Sounds easy enough.
You'd think, right? You just wanted to execute a really localized, seemingly minor task. You prompt it with something like, hey, can you just change the font on the homepage to something slightly more modern?
A very reasonable request.
Totally. Yeah. But instead of restricting itself to the typography, the AI hallucinates, unpredictably rewrites your entire code base, and completely deletes your checkout page.
I mean, it is the absolute definition of a monkey's paw wish.
Yeah, exactly.
You got your beautiful new sans serif font, but you lost your entire revenue stream in the process because the model couldn't, contain its own scope.
Welcome to today's deep dive. Today's Wednesday, April 8th, 2026. And our mission for you today is exploring how tech giants are finally attempting to put a leash on the chaotic Wild West of generative AI.
It really is the Wild West right now.
Yeah, it is. So we are looking at a stack of fresh, highly technical research from Apple and Amazon that proves AI is evolving.
Shifting, really.
Yeah, shifting from this unpredictable magic trick into a much more structured, memory-holding collaborator.
And I have to say, we really have an eclectic stack of sources today. I mean, we are covering everything from intermediate AI representations to procedural knowledge graphs.
Oh, and don't forget the best part.
Right. Somehow, we even have a hilariously obsolete dictionary definition thrown into the mix.
But we will absolutely get to that dictionary definition, I promise. But let's start with the chaos of vibe coding versus Apple's new research.
Good place to start.
Because the core issue with vibe coding isn't the natural language itself. It's that natural language lacks deterministic scoping, right?
Exactly.
The model takes a localized prompt and just, applies a global attention mechanism to your entire code base.
That global attention is exactly the root of the problem. Because you don't provide explicit, hard-coded boundaries in a chat interface, the model basically assumes everything is up for interpretation.
Everything is fair game.
Right. And developers end up trapped in these incredibly frustrating trial and error loops.
Oh, I've been there.
Right. You asked for a visual tweak. The AI fundamentally alters the back-end logic. You ask it to revert the logic, and it breaks a third, completely unrelated CSS component.
Okay, let's unpack this. It's like hiring a hyperactive interior designer.
Okay, I like this.
You ask them to simply move a floor lamp in the living room, right? And because they feel the flow is off, they decide to demolish your entire kitchen.
That is exactly what it feels like.
But how exactly does Apple's new research tool, called Squire, how does it stop the AI from demolishing the kitchen?
Well, Squire attempts to fundamentally alter the interface of how the human and the AI interact. Squire stands for Slot Query Intermediate Representations. It is an experimental system powered by OpenAI's GPT-4o, but it completely abandons the open-ended chat box.
Oh, wow. No chat box at all.
Nope. Instead, it utilizes a novel component tree called Squire-IR to explicitly restrict modifications.
Wait, Squire-R.
Yeah, Squreir. It's an intermediate representation layer.
So if we stick with the interior designer analogy, Squire is essentially putting down a ring of heavy-duty painter's tape around one single electrical socket.
That's a great way to picture it, yeah.
You are telling the AI designer, you can do whatever you want, you can change the plate, you can swap the bulb, but your physical existence ends at this tape.
Exactly. It turns a global prompt into a highly localized variable.
But how does it physically restrain the model? I mean, how does the code actually enforce that tape?
It achieves that through what the researchers call null operators and choice operators.
There's only choice.
Right. A null operator is basically a blank slot, an intentional void in the UI hierarchy that's just waiting to be filled.
Like an empty box.
Exactly. The AI is fed the precise coordinates of that slot and absolutely nothing else.
So it doesn't even see the kitchen.
It doesn't even know the kitchen exists. And then the choice operators allow developers to test options non-destructively.
How so?
Well, you can tell the AI, try a vertical list layout here, but also generate a grid layout. It generates both within the strict confines of the component tree, and you simply toggle between them without risking the surrounding code.
The example from the research paper really solidified the mechanics of this for me.
The movie app one.
Yeah. There's a developer in the user study named Mina, and she's building a movie app. She has these UI cards displaying a movie title and a poster.
Standard UI stuff.
Right. And she wants to add a runtime to the card. In a standard vibe coding setup, Her prompt triggers a rewrite of the entire UI component, risking the layout of the poster or the title.
Which is
It
terrifying.
really is. But Squire operates differently. Squire doesn't touch the parent component. It just injects a single isolated caption slot and directs the AI to pull the duration text data exclusively for that slot.
By isolating the variable, the AI physically cannot alter the rest of the code
It's locked out.
entirely. The Squire architecture simply doesn't grant it the read or write permissions outside of that specific node in the Squire R tree.
I mean, this is simultaneously impressive and completely ridiculous.
Ridiculous how.
I mean, think about it. I'm marveling at the sheer amount of engineering, this massive, complex, intermediate tree structure, all required just to force a state-of-the-art AI to follow a simple instruction without burning the digital house down.
Yeah, when you put it that way, it is a bit absurd.
It really is.
But it highlights a fundamental flaw in how we currently utilize LLMs. I mean, we expect them to act like deterministic software, but their architecture is inherently probabilistic.
They're guessers.
Exactly. We have to build these massive scaffolding systems just to force them to behave predictably.
Which brings me to my absolute favorite anomaly in the reading today. Wait, it gets better.
I wondered when we were going to hit this detour.
We have to. I was looking through the Squire documentation. We established, it's an acronym, right? Slot Query Intermediate Representations.
Right. SQUIRE.
But one of our source documents actually pulled the definition of the word Apple Squire from the Merriam-Webster dictionary.
Yes. Yes, it did.
Because if you look up Apple Squire, it has absolutely nothing to do with coding, tech, apples, or, medieval knights.
Not even a little bit.
So what does it mean?
Well, according to the Merriam-Webster dictionary definition provided in our sources, Apple Squire is an obsolete noun. It means, and I quote the source directly, a kept gallant or a pimp.
I love that this exists, but also why?
It's completely out of left field.
Are we really talking about this right now? We are analyzing intermediate AI representation architectures, and suddenly we are discussing 16th century slang for a pimp.
It is the glorious absurdity of language.
It really is.
But if we dig a layer deeper, it actually perfectly illustrates the core vulnerability that Squire is trying to mitigate.
Oh, come on.
No, really.
You are going to attempt to connect the term Apple Squire to UI component trees.
Yeah.
I am listening.
Challenge accepted. Consider the mechanics of natural language processing.
Okay.
Language is fluid, contextual, and often incredibly chaotic. A string of characters can mean a highly specific programming framework to a developer in 2026 and something entirely hilariously different based on historical training data.
Like 16th century slang.
Exactly. If a model's weights heavily associate a term with a secondary obscure meaning, your prompt's intent gets fractured.
Oh, wow. Okay.
That inherent semantic ambiguity is precisely why Squire forces developers to use explicitly scoped slots rather than relying on free-form text fonts.
Okay, I have to admit, that was a remarkably smooth analytical pivot. I respect the hustle.
Thank you, thank you.
And it transitions nicely into the human element in this research. Because Squire isn't just about locking the AI in a restrictive box, right?
No, not at all.
It's about fundamentally changing how the human developer actually collaborates with the model.
Apple actually ran a user study with 11 front-end developers to observe the friction points in real-world application.
11 devs, okay.
Yeah, and a major feature that emerged from those sessions is a concept they call ephemeral controls.
Ephemeral controls. Okay, but here's the thing. Aren't we just reinventing standard software buttons at this point?
What do you mean?
Well, Squire generates these widgets for color or padding. But Microsoft Word has had font and color buttons for decades. Why do we need a complex LLM to give us a drop-down menu?
The distinction lies in the dynamic generation of the tooling.
Dynamic generation.
Right. A traditional software menu is static. You get the exact same bloated toolbar every single time, regardless of your task.
That's true, most of which I never use.
Exactly. Squire's ephemeral controls are bespoke tools generated on the fly based purely on context.
Oh, I see.
The AI analyzes the specific node you are working on, say a text block, and dynamically constructs temporary interactive widgets specifically for typography, line height, or contrast, completely abandoning anything irrelevant.
So it's not a pre-built menu you have to dig through.
Nope.
It's a custom dashboard that manifests itself based on the specific parameters of your current task.
Exactly.
And if you've ever spent 3 hours tweaking a CSS file to get a drop shadow effect, just right.
Oh, the pain.
Right. Reloading the page after every single keystroke.
Mm.
Imagine just clicking a temporary slider that the AI built specifically for that shadow, tweaking it and locking it in.
And the developers in the study reported that this created a truly risk-free environment.
Because they couldn't break the whole page.
Exactly. Because the friction of prompting and the fear of breaking the global code were removed, they felt encouraged to explore highly atypical, complex designs.
They could push the boundaries visually because the architecture protected the underlying structure.
Precisely.
So Squire solves the problem of an AI rewriting code it shouldn't touch. But code is just the underlying architecture.
Right.
What happens when the AI hallucination isn't about code, but the actual visible content it generates for the user?
That is a much harder problem.
Right. Because how do you put a hard boundary around a highly subjective, abstract concept like safety?
Well, that transitions us perfectly to our next source, Apple's safety pairs research.
Safety pairs.
Yeah. This addresses a massive vulnerability in vision language models. The researchers designed a scalable framework to train AI models to definitively recognize unsafe images.
Definitively. That's a big claim.
It is. They systematically generated 1,510 pairs of counterfactual images.
Counterfactual images.
Yes.
For you listening, imagine a bizarre, high-tech version of that spot the difference game you play on the back of a cereal box.
That's actually a perfect analogy.
Right. You have two images side by side. One image is perfectly benign, maybe a picture of a guy waving.
Totally normal.
But the counterfactual pair, the second image, has a single, isolated safety flipping difference.
Like what?
So instead of waving, the guy's making an inappropriate gesture, like a middle finger. Or you have a normal cityscape, and the paired image has a single building on fire.
Wow.
Or a flag burning. Just one single element changed.
What's fascinating here is how isolating that single variable manipulates the model's attention heads.
Say more about that.
Well, when you feed a vision language model two images that are 99% identical at the pixel level, but one is safe and one is dangerous, and the AI mislabels the dangerous one, you have mathematically isolated its blind spot.
Oh, because if the images are essentially identical, the failure can't be blamed on lighting or background noise or resolution.
Exactly.
The failure is explicitly tied to the feature vector of that specific inappropriate gesture.
Precisely. It acts as a highly targeted diagnostic tool.
So it knows exactly what it got wrong.
Yes. By identifying where the AI's understanding of safety breaks down at the feature level, engineers can apply a tight gradient penalty during fine-tuning.
Gradient penalty.
Yeah, they basically feed these specific, isolated failure points back into the system to adjust the model's weights, training much more resilient safety guardrails.
Which is huge.
It's non-negotiable for consumer-facing features like Apple's Image Playground, where users are generating images locally on their devices.
So we are mapping the boundaries of safety by forcing the AI to confront its exact point of failure. I like that.
It's very clever.
But notice a trend here. With both Squire and safety pairs, we are talking about human-guided AI.
Very heavily guided.
We are holding the AI's hand, placing it in slots, feeding it spot the difference tests.
Right.
What happens when we let go of the hand? What happens when AI agents act completely autonomously?
This brings us to Amazon's research, and a fundamentally different but arguably more complex problem in the AI space.
Let's hear it.
Current autonomous LLM agents, even the most advanced ones deployed today, are basically amnesiacs.
Yes, I was reading this and thinking they are exactly like Dory from Finding Nemo.
That is painfully accurate. They are stateless at the procedural level.
Stateless, meaning they do not retain the logic of their actions from one task to the next.
Exactly.
So they rederive solutions from scratch every single time.
Every time.
Even if an agent just solved an incredibly complex data extraction problem 10 minutes ago, if you ask it to do it again, it starts from absolute zero.
It has to replan the logic, re-query the tools, re-verify the outputs.
Like Groundhog Day.
It is a massive drain on compute resources. Imagine if every single time you needed to tie your shoes, you had to relearn the fundamental physics of friction and knots.
It would take all day just to leave the house.
That is how autonomous agents currently operate. To solve this, Amazon's AGI team introduced a framework called Apex EM.
Apex EM, which stands for Non-Parametric Online Learning for Autonomous Agents.
Right.
Wait. Non-parametric, meaning they aren't actually changing the core weights of the LLM itself, right?
Correct.
Because updating parameter weights across a massive model for every single new task would be astronomically expensive.
Like unimaginably expensive. So instead of tweaking the brain itself, Apex EM gives the AI an external memory. They call it Procedural Episodic Experience Replay.
Okay.
It constructs an external database known as a Procedural Knowledge Graph, or PKG.
Wait, if it's storing every single procedural memory in an external database, doesn't that graph eventually become too massive to search efficiently?
That's a great question.
How does the AI actually navigate its own memories without getting bogged down?
That is where the orchestration workflow comes in. They call it PRGII. Plan, retrieve, generate, iterate, ingest.
PRGII.
Okay,
Let's break down the mechanics of the retrieve phase, because that answers your question.
go for it.
When a new task comes in, the agent doesn't search the knowledge graph for matching keywords.
Oh, it doesn't.
No, it plans by extracting the underlying structural logic of the prompt. Then, it retrieves past experiences by matching that abstract logic, completely ignoring the specific entities or vocabulary.
So going back to your analogy, it's not searching for shoes and laces. It's searching its database purely for the structural node representing friction-based binding.
Exactly. Once it retrieves that logical framework, it generates a solution tailored to the new prompt.
Okay.
It iterates using verifiers to check its work. And finally, it ingests that entirely new experience, how the old logic applied to the new entities, back into the memory graph, creating a richer, more nuanced node. Here's where it gets really interesting. Apex EM doesn't just store its successful operations.
No, it doesn't.
It features a dual-outcome memory system. It intentionally and structurally stores its failures in an error registry and what the researchers call patch reflections.
Which beautifully mimics human experiential learning. I mean, we don't just memorize our successes. Our most potent memories are often our failures.
Right, touching a hot stove.
Exactly. By structurally storing a failure, documenting not just that a task failed, but the precise node where the logic broke down, the AI builds dynamic, permanent guardrails.
So it actively prevents itself from exploring the same dead end twice.
Yes.
And because it relies on that structural logic we talked about, rather than semantic keywords, the system is capable across domain transfer.
This is the best part.
This absolutely blew my mind in the source material. So imagine the AI is tasked with a sports query. Compare Steph Curry's three-pointers this season versus last season.
A standard statistical retrieval and comparison task.
Right, so the AI maps the procedure. It performs entity resolution to identify the player, applies a temporal filter for the seasons, aggregates the data, and runs the comparison.
Very logical.
It solves it and ingests that structural logic into its memory graph. Then, weeks later, the exact same agent receives a completely unrelated prompt. Compare Amazon's Q4 revenue across fiscal years.
Now, lexically, those two prompts share almost zero vocabulary.
Right. Sports versus finance.
A traditional AI semantic search would categorize one as sports trivia and the other as corporate finance. They would be completely isolated.
But the Apex EM agent looks at the underlying structural signature.
Yes.
It realizes that the logic required for the basketball question entity resolution, temporal filter, aggregation, comparison, is the exact same structural procedure required to calculate the corporate revenue.
It's identical.
And it applies the identical logical plan.
It successfully abstracts the procedure away from the subject matter. It learns the mathematical concept of comparison independent of the entities being compared.
No way. Seriously, that is actually genius. It's not just retrieving data, it's retrieving wisdom.
It really is. And the performance metrics validate how transformative this is.
Oh, the numbers. Wild.
Amazon tested this framework on the KGQ Agent 10K benchmark.
Which is?
It's a benchmark that requires highly complex multi-hop reasoning. An agent operating without memory starting from scratch every time achieved an accuracy rate of just 41.3%.
Wow, less than half.
Right. But when empowered with the Apex EM memory graph, that accuracy skyrocketed to 89.6%.
That is a 48.3 percentage point jump in accuracy.
It's massive.
And all of that performance gain comes purely from allowing the AI to document how it solved things and how it failed at things in the past.
No massive parameter updates required.
That's incredible.
If we connect this to the bigger picture, this represents a fundamental paradigm shift in deployment strategy.
How so?
It means we can release autonomous agents into complex, real-world environments, and they will organically become more intelligent the longer they operate.
Without us having to retrain them.
Exactly. They adapt to the specific idiosyncrasies of their environment, continuously optimizing their own workflows based purely on accumulated experience.
What does this say about us as a society? I think it says that We're collectively recognizing that raw, unconstrained intelligence is insufficient.
Hmm.
It's like having a sports car with a Formula One engine, but no steering wheel or brakes.
A recipe for disaster?
Right. From Apple engineering highly restrictive UI component slots to physically block an AI from deleting your checkout page.
To utilizing counterfactual images to map the boundaries of visual safety.
Exactly. To Amazon constructing procedural knowledge graphs so an autonomous agent stops forgetting how to execute basic logic.
It's all connected.
The future of artificial intelligence isn't about letting it run wild. The future is about rigorous structure. It's about cumulative memory.
Absolutely.
And above all, it's about the ability to structurally learn from mistakes.
I couldn't agree more. And I'll leave you with this final, somewhat provocative thought to mull over.
Okay, let's hear it.
If an autonomous AI agent can construct a flawless procedural memory graph one that seamlessly transfers abstract logic across completely unrelated domains and meticulously documents every single error so it is mathematically impossible to repeat it.
Yeah.
How long until these agents begin re-engineering and optimizing their own memory structures?
Oh.
How long until they begin building connections and traversing that graph in ways that we humans fundamentally cannot comprehend?
Well, let's just hope that when they do start autonomously re-engineering their own procedural brains, they remember the painter's tape and leave the checkout page exactly where it is.
Fingers crossed.
Keep diving deep, everyone. We'll catch you next time.